Here we're going to be getting into using those conversion factors that we've practiced previously, except this time we're going to be using them not just for individual atoms or elements, but for going from one element to another element. And we can also do it to figure out how much of each of these we need to make that and vice versa. And so let's get into it. Now, all of this works because of something that I've mentioned before, which is the law of conservation of mass and matter. It's why we balance a chemical reaction equation, because we cannot, it is not allowed to create or destroy matter in a chemical reaction. We will get into nuclear chemistry a little bit, and when we do that, you'll find that those are physical reactions. We can do that because of Einstein's E equals mc squared, but in a chemical reaction, we start with a certain number of atoms, we end up with the same number of atoms, and so there's no change in the number of pieces, there's no change in the mass, and so because there's no change in the pieces, sometimes it's called the law of conservation of matter, but what that means is that the mass of the reactants and products are equal to one another. And so here, for example, and they've shown you the precise values here, we have a certain amount of each of those reactants, 215.8 and 32.1, and they end up with 0.9724. And so notice they are equal. Now, I'll be honest, when you're doing a chemical reaction, this isn't usually how it exactly goes, because there's going to be mistakes made in the lab. There's going to be some of this that doesn't get made because not all the pieces reacted, or they weren't well mixed, or you lost some. But if we were able to capture all those pieces we lost, we could be certain that we had the exact same mass and stuff. We start with a certain number of pieces. We have to end with the same number of pieces. If the starting parts have a certain mass, the ending parts, they have the same mass. It's just that they're rearranged through the reactions we talked about previously. And so here they show that a handful of ways. One is if we had just individual atoms reacting. Another is if we had a proper ratio based off of 100 pieces reacting. Another is having an Avogadro's number's worth. Well, an Avogadro's number worth is the same thing as a mole, and a mole is the same thing as the mass, and so this works out. And so it takes a certain amount of mass of reactants, and we end up with the same mass of products. And these things up here are not something that we can easily measure in the lab. The mass is, but because the mass of each element, the mass of each atom is different, then we end up having to bring them into a common grounds where we know we have the same number of atoms of each, and so moles is our middleman where we do that. So here we have a reaction equation that they balanced for us already, and we have our coefficients 2, 3, and invisible 1 there. Well, we can read that as a particular number of moles of each of those are necessary to make it. And so then each one of those can become a conversion factor, a ratio that we can use. And that arrow is a little out of place. It really should be down here. But of course, anytime we have two equalities where those are equal, we can then relate them as having either one in the numerator or denominator. But here are once again conversion factors that are based off of the individual atoms or elements involved, based off of the number of pieces we have. And so we really just have the one conversion factor, moles over moles, but because there are so many different reactions, it results in just a lot of different ones. Here is an example, and we're asked to find which one of these are correct conversion factors. So the first one here is hydrogen and nitrogen. We can see that the coefficient with hydrogen is 3 and with nitrogen is invisible 1, so we're looking for a 3-to-1 ratio. So that one's right out. From there we need the 3 to be with H2, so that is that one. Here for NH3 and H2 we're looking for a 2 to 3, so that one's out. And then 2 goes with NH3, so it should be. This question here asks for moles of Fe2O3, so that's what we're going to be solving for, from 6 moles of O2. So we're going to start always with the value that we're given, and then we're ready already for a conversion factor to turn moles of oxygen into moles of iron oxide, specifically iron 3 oxide. And you recall previously I have said that anytime we have moles above or below something else, the number for it is 1. However, this step here is what I will call the stoichiometry step. That is the new concept here, and we're simply relating two different chemicals. Stoichiometry simply means to count atoms or to count pieces of molecules, and so we have moles over moles. It is possible that the coefficient there could be 1, but here we have 2 moles of Fe2O3 and 3 moles of O2. And so those are our conversion factors. Our moles of O2 are going to cancel out with one another, and we're left moles of Fe2O3, which is what we wanted. And so that's going to end up being 4.0 moles of Fe2O3. Here we're given another practice calculation over this, and this time it's the same reaction equation, except we have 12 moles of oxygen to start out with. And so we have 12 moles of O2. And we know that there are 3 moles of O2 that came from the reaction equation up here for every 4 moles of iron. We are asked how much. I didn't specify that specifically, but 4 moles of iron. So here we know the amount of one reactant we have, and we need to know how much other reactant we want. And so then this ends up being 16 moles of O2, which matches that one, and I should have written it with proper sig figs. It is 16.0 with 3 sig figs here. And so we can compare reactants to one another, reactants to products, or we didn't have an example of this, but products to one another as well. In the next section, we're going to look into what I mentioned a moment ago, that in the lab we can only measure grams, and so we're going to look at how we take grams and turn them into moles. But that finishes up this section.